First of all, let me tell you what all parts are we going to cover here, right? So in this chapter, in hydrocarbons, we shall take up alkanes, alkenes, and alkynes, and even some cycloalkanes and cycloalkenes, etc., all of that. In each category, and in aromatics, we would take up benzene. These are the four topics that we have to take up. Now, in each category, here, we would be talking about preparations. How are they prepared? We would take up physical properties. And we would take up chemical properties also. So preparations, physical properties, and chemical properties, all of that together. Now, let us take up the first part, and that is alkanes. In alkanes, we take up preparations. And in preparations, we start with first from alkenes, alkynes, and cycloalkanes. We're trying to prepare normal alkanes from cycloalkanes. How do we get that? Again, all of that together. Pay attention. Any alkene or alkyne, for example, if there's an alkene or if there's an alkyne, you just need to add H2. You add H2 here, or you add 2H2 here. And what you get is C, H and H, and here you get C, H, 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 H. So you can see that for every pi bond broken, you give one hydrogen to carbon and one hydrogen to this carbon. So break one pi bond and then give one hydrogen to carbon, one hydrogen to this carbon. Here there are two pi bonds broken. So for every one pi bond you allot one hydrogen. Two pi bonds broken, you have to give two hydrogens. Now this reaction is not easy. You need a catalyst without which it won't happen. So what are the catalysts used? Here you can have PT or PD or Rene nickel. Any one you can use, PT or PD or Rene nickel, and the reaction occurs at room temperature. And the same here as well. This reaction is called hydrogenation. The reaction is called hydrogenation. The reaction is called hydrogenation. Is that okay? Right. So this here that we're doing here is hydrogenation. Addition of hydrogen is called hydrogenation. The pi bond breaks and each carbon gets one hydrogen on it. For every one pi bond broken, one hydrogen added. Is that okay? Clear, right? Okay. Now, let us take up some simple examples. And before doing that, let me do this. If catalyst used is nickel, not Rene nickel, simple nickel. If the catalyst used is simple nickel, in that case, high temperature and high pressure are needed. High temperature and high pressure are needed, and the reaction is referred to as Sabatier-Senderin reaction. Sabatier-Senderin reaction. So, the reaction in general is called hydrogenation. However, it depends on the catalyst. If you're using PT, PD or Rene nickel, the reaction can be carried out at room temperature, and the reaction would be called and if the reaction is carried out in presence of simple nickel, normal nickel, it will be called Sabatier-Senderin. And Sabatier-Senderin conditions, the reaction has to be done at higher temperature and pressure conditions. Okay, everyone? All right. Now, pay attention. After having done this, let me give some specific examples. The first example we can take up is this. And if I carry this reaction out in presence of H2 in presence of, let's say, PT, PD, PT, anything, the pi bond breaks and we get cyclohexane. If you take a normal double bond like this, H2 plus PT gives us the normal alkane. So but 1 in gives butane. Cyclohexene gives cyclohexane. Right? And if I do this reaction in presence of only nickel as a catalyst, if I'm doing this in presence of H2 and Ni, then you need high temperature and pressure. This would give you which is, a simple reduction reaction. And this reaction, the last one that we did, is called Sabatier-Senderon reaction. If you are using a triple bond, then, for example, if you have a triple bond here, let's say R, C, triple bond C and R, is this okay now? Yeah. So here you would need two H2s, not one, and you can use a catalyst like PT or anything, and it would give you R, C, single bond C and R. Now rest of the valencies are fulfilled by hydrogens. And this is nothing but an alkane. So your triple bond is supposed to be, broken down, and for every pi bond broken, there is one H2 added. So you have two hydrogens added, and this is how you get an alkane. One more thing that you have to understand here is, whenever you use this alkene, and if you try to perform reduction, right, with hydrogen, remember this is the matrix of metal. This is the metal surface, and the hydrogen molecule always stays connected to the metal surface. It is absorbed on the surface of metal. What I want to talk about here is, when hydrogen adds, as it is going to attack that C double bond C, it attacks from the same side. See, whenever addition reaction occurs, it is very important for you all to know whether the addition is taking place from the same side or from the opposite sides. This is an example where addition takes place. See, if this is a double bond, hydrogen would attack from the same side. This is called syn addition. Now here, it might not play a very big role in knowing whether it is syn addition or some other addition, right? But later on, you will feel the need of knowing this, because without that, you may not be able to do a certain things. So here I'm going to put this as, this is syn addition. Or let me put this here. So here I can put up a note that hydrogenation in presence of metal catalysts is syn. So this is syn addition, an example of syn addition. Syn is from the same side. If you want to make a note of that, you can always make a note of that. From both hydrogen atoms, approach from same side. Both hydrogen atoms approach from same side. That is syn. Okay, so you have to know this to the perfection. One more thing. If you take up okay, so if you take up cyclopropane or cyclobutane, these are highly strained molecules. The reason being, what is the bond angle here? 60. What is the bond angle here? 90. What is the hybridization of the carbon out there? sp3. This is also sp3. What is the regular bond angle for sp3 hybridization? What is regular bond angle? 109.5. That's a regular bond angle. And here, what do you see? The bond angle is very, very strained. One has become 60, one has become 90. So these molecules are highly strained molecules, and any strained molecule would always want to open itself up, relieve itself from the strain that it is subjected to. So what happens then? Pay attention. Only these two, if I treat them with H2 in presence of PD or PT or whatever, there is bond breaking taking place here. Any one of these bonds break, open. It breaks open. And this would become, so a cyclopropane would open up and become propane. Cyclobutane would open up and become butane. Right? What is the general formula of cycloalkanes? Cycloalkane is CnH2n. Any cycloalkane would belong to which general formula? CnH2n. And any alkane, what is its general formula? CnH2n plus 2. So what are you adding now? You are adding 2 hydrogens so that a cycloalkane becomes a normal alkane by adding 2 hydrogens, breaking the bond. Right? Just remember one thing. Above reactions are not observed with cyclopentane or cyclohexane. All right? Okay. Now, the second reaction is from alkyl halides. There are many different ways by which alkanes can be prepared from alkyl halides. So, pay attention. We would take up the first one. The first reaction is by reduction of alkyl halides using zinc. Reduction of alkyl halides using zinc. Right? Ideally, what we could do is we could take Rx. We could take Rx and we could react Rx with 2H. This is like nascent hydrogen. When I put H in bracket, it is nascent hydrogen, a very reactive form of hydrogen, a very, very reactive form of hydrogen. So ideally, this can give you RH plus HX, and RH that you get is ideally an alkane, and this is, X can be chlorine, bromine or iodine. With fluorine, the bond is strong and does not break easily. Now pay attention, where do you get this nascent hydrogen from, right? So I'm going to show you how this can be done. So this nascent hydrogen can be obtained by taking zinc with acetic acid. One of the ways. The same can be obtained by taking zinc with HCl or H2SO4. The same we can get by taking zinc with NaOH, or we can even have, not exactly the same, but yeah, what you could do is, these are all different ways of getting nascent hydrogens. So 3 systems that I'm going to show you here, right? They all produce the same thing. Now pay attention. The fourth thing that you could probably use, which would not produce nascent hydrogen, but remember, zinc and copper alloy with ethanol. This can also be used for same reaction. So it is this system is a little different, but you still can use all of this. Although it may not produce nascent hydrogen, so I'm not putting it exactly along with nascent hydrogen. But yes, can be used for the same thing. Right? Okay. Now pay attention. I can give you some specific examples before we do anything else. Again, look at this. And one more thing, reactivity order. Reactivity of Rx. Here it is Ri greater than RBr greater than RCl. This is the reactivity order for the same. Is that okay? This is the reactivity order. Clear? All good? One more thing here, pay attention. We would be discussing the mechanisms also. Eventually, we would talk about how this exactly happens, but for now, we are just doing disconnections. Okay, now pay attention. We can take up some specific examples, and you can start by taking, for example, CH2Br in presence of, let's say, Zn plus HCl, giving you CH3. You can even take a simple CH3, CHBr, and CH3. And if you use a simple Zn plus NaOH system, it could probably give you once again the same thing: CH3, CH2, CH3. Some basic examples where every time we disconnect halogen and replace it with hydrogen. Right? We disconnect it and replace it with hydrogen. Now pay attention. Here, Rx, the second method that we can probably put up here would be catalytic hydrogenation. Catalytic hydrogenation. Oh, here you take Rx and react it with H2 in presence of especially PD. PD is more often used, but catalytic hydrogenation would give you RH plus HX. So again, all these methods are used for primary, secondary, or tertiary alkyl halides. Generally, this Rx, it can be primary, secondary, or tertiary alkyl halide. Any of these, right? So that's catalytic hydrogenation. So we have one which is by reduction of alkyl halides using zinc, and this is the second, catalytic hydrogenation. The third thing that we have now is reduction using hydride donors. First of all, what is hydride? H minus, hydride donors. So now we are trying to carry out reduction using hydride donors. Let us take up this. So we take up Rx, and any hydride donor would give you H minus. Now H minus would always attack the partially positive alkyl group, and it would always attack this. And the two electrons of the bond, there would be heterolytic fission, two electrons of the bond, they are taken by X, and what you get here is RH, which is an alkane, plus X minus. This is an alkane. Are you clear? H minus would try to come in and X minus is pushed outside. Now, pay attention. Here, the sources of hydride. First source is a very important source, LiAlH4. This is called lithium, aluminium hydride. And it can be used for primary and secondary Rx. Very important, and you all have to make a note of this. Lithium aluminium hydride is used for primary and secondary Rx. Primary alkyl halides and secondary alkyl halides. So if you want to get H minus, lithium aluminium hydride can give you H minus. What is the next thing that we have? The next thing that we get is NaBH4. NaBH4 is used for secondary and tertiary alkyl halides. This is called sodium borohydride. These are the most commonly used hydride donors used for reduction of alkyl halides. The third thing that you could probably have, which is lesser known but very effective, is PH3SNH. This is called triphenyl tin hydride, and this is used for primary, secondary and tertiary RX. So this is the most versatile of all of them. Most versatile of all of them. યાદ રાખવાનું, all hydride donors, note, all hydride donors do not affect isolated C double bond C. Very important, they cannot affect C double bond C which are isolated. I would be telling you when will they affect under specific conditions, right? So that I would show you later on. But under normal conditions, they would not affect C double bond C. Is this okay? Clear? Fair. Now pay attention, some examples we do. CH3 CHBr CH2Br. What kind of carbon is this here? What kind of carbon is this here? Primary. So it's a primary alkyl halide, this part here. What kind of carbon is this? Secondary, so that's a secondary alkyl halide. Now if I'm going to use, let's say, sodium borohydride here, NaBH4, whenever we use NaBH4 or LiAlH4, the second step would be like, water or H3O plus, anything you want. What would happen here? Pay attention. Did we write that sodium borohydride can be used for which alkyl halides? So here, do we have a primary alkyl halide? Which part is primary? This is a primary alkyl halide and this is a secondary. So where would the reaction come? On secondary. Perfect. So here it would react and break this bond. So then we'll have CH3, CH2, CH2 and Br. Why? Because primary is not affected, only secondary gets affected. Is this okay, everyone? Another important thing. Suppose if I put and if I use 1 LiAlH4 and 2 if I use H2O. what am I going to get? There would be bond breaking taking place here. Will double bond be affected? I have already mentioned that double bond will not be affected. All hydride donors do not affect isolated double bonds. So the double bond would remain as it is. However, if the same reaction, if I would have carried out in a different way, for example, if I would have used H2 plus PDC, palladium carbon, like what we have here, palladium carbon, you can put PDNC carbon here. Right? It can also remove X and replace it with hydrogen, right? It can also do the same thing. But palladium carbon would also affect double bond. See, double bond C is also broken down. Did we see that in the first reaction? Alkenes can be converted into alkanes by adding H2 using PD, PT or Ni. So if you are using PD, then what would happen? Your product would be something else. Even the double bond is converted into a single bond and hydrogens given to it. So while first one has double bond retained, the second one does not have double bond in it. Are we clear with this? All okay? समझ में आवी हुआ बराबर? So this was the third way of reducing alkyl halides. For those who are going to do only boards later on, should do only the first process. Second and third are not to be done if you are going to do only boards. So make a note of this as well, right? I'm going for the fourth process. Pay attention. The fourth process that we need to talk about is Wood's reaction. Let us try and understand the Wood's reaction. Okay, pay attention. Let us try and figure out what Wood's reaction is all about. Okay, so I'm not giving you the mechanism because mechanism I would be doing this later on because this mechanism is a free radical mechanism, more accepted mechanism. There is also an ionic mechanism given, but free radical is more accepted mechanism. Okay, but yes, I can quickly show you how this works. You can have an alkyl halide. Pay attention. But this alkyl halide where X can be chlorine, bromine or iodine. And remember, it should be, note, tertiary alkyl halides are not preferred. Tertiary alkyl halides are not preferred. So here what we do is, we take two sodiums there is this Rx, 2 moles of Rx and 2 moles of sodium here, as I've shown here, and the solvent used is ether and heat, and you see that you get R and R plus 2 times NaX. This is an alkane formed. So alkyl halide gives alkane, but if you look at the alkane, what exactly do we get? alkyl halide only one R here and your alkane has two R's. What does that mean? We can say alkane formed has twice the number of carbons as found in alkyl halide. So your alkane will have twice the number of carbons as are found in alkyl halide. I can take a regular example and show you how this works. Suppose if I take CH3Br 2 times, so plus 2 times Na plus Br and CH3. Then what do we get? We get CH3 and CH3 plus 2 times NaBr. We started with methyl bromide and we end up in getting ethane. Did you understand this? If you take up something like this, 2 times, and if I ask you to get, 2 sodiums and ether, can you give me the product? Can you give me the product? How would you give the product? Right? It would, if in simple form, you could probably put it like this. You could probably put it like this. In simple form. All okay? Otherwise, what is this? The name is, this was 2-bromo butane, and this is like 1, 2, 3, 4, 5, 6. 3,4 dimethyl hexane. Do you all agree to it? Double the number of carbons you get. And minus 2 NaBr if you want to put, it is fine. Otherwise, it is also okay if you forget. All clear? Suppose I put it up like this, that you have Rx treated with 2 moles of sodium in ether and heat, and suppose your product formed is, let's say, and if I ask you, therefore, Rx is equal to what? Now, it is a very simple thing. In Wood's reaction, you always get a symmetric product, which means it will be a product which can be equally divided into 2 parts. It would be a product which can be easily divided into 2 equal parts. So here, you may have your product getting divided into 2 equal parts. Right? So Rx should be what? It should be 2 of these must have reacted to produce the given product. You just break the product in it should always be a symmetrical structure. So divide it into two equal parts and you will be able to know what your R is, the structure of R. Do you get this? Okay. Now, let me go to one of the problems of Wood's reaction. Right? I'm going to go to the problems of Wood's reaction. Pay attention. Is this okay? Now, imagine I had to do this. I'm trying to do a Wood's reaction, but this time not taking the same alkyl halides, but using two different alkyl halides. Can anyone tell me what product should I get? Can anyone tell me what product should I get? The most expected product should be propane, CH3, CH2 and CH3. The most expected product is propane. But pay attention. Here, suppose if I ask you to do this reaction in a laboratory, how would you do this? You would probably start by taking 1 mole of ethyl bromide. 1 mole of ethyl bromide is about, let's say, ethyl group is I think 29 plus, it's a 30 plus 80 would be 119. So you have to weigh 119 grams, 1 mole, 119 grams of ethyl bromide and put it in your flask in which you want to do the reaction. Then what else do you have to take? Sodium, metal and put it inside the flask. So sodium metal, each sodium is 23 grams per mole. 2 of them would be 46 grams. So take 46 grams of sodium and put it in the flask. And what else? You need 1 mole of CH3Br. What would that be? 15 coming from CH3 and Br is 80, so 95 grams is the molar mass. 95 grams of CH3Br altogether. Now, I put some ether as a solvent and I start my reaction. Is it compulsory for me, or is it possible that I can ask all methyl bromides to go and find ethyl bromides and react? Can I program it in that way? No. Is it not possible that any methyl bromide may not come in contact with ethyl bromide, but before it comes in contact with ethyl bromide, it comes in contact with another methyl bromide and reacts with it? Yes. Is it that every methyl bromide has to? 1 mole is 6 into 10 power 23 molecules. So there are 6 into 10 power 23 molecules of ethyl bromide, 6 into 10 power 23 molecules of methyl bromide also. Is it possible that every time a methyl bromide has to search for a methyl bromide and then react? Is it not possible that a methyl bromide may come across a methyl bromide and reacts with it? Is it not possible that your ethyl bromide may react with one more ethyl bromide and react with it? It is absolutely possible. So there are 3 possibilities. One possibility is your desired product, which is your propane. But the other thing that you could probably get is 2 ethyl bromides react with each other and they can produce what? They can produce butane. And 2 methyl bromides can react and produce ethane. So here you are getting 3 products: butane, propane and ethane. This is ethyl bromide and this is methyl bromide. So while one is ethyl bromide, the other is methyl bromide, and you end up in getting 3. So If I intend to get pure propane, am I going to get a pure propane? Never. In Wood's reaction, it is not possible. So what is the biggest disadvantage of Wood's reaction? What is one of the biggest disadvantages of Wood's reaction? One of the biggest disadvantages of Wood's reaction is that we cannot prepare an alkane with odd number of carbons in pure form. See, if you want an alkane with even number of carbons, maybe you manage it. Because there you will have to use only same kind of alkyl halides. But if you want an alkane with odd number of carbons, you may have to use two different types of alkyl halides. And in that case, you may not get a pure product. You may end up in getting three products. Do you understand this? So what is the disadvantage of Wood's process? Limitations. One, alkanes with odd number of carbons cannot be produced in pure form. Three products are generally formed. Can you think of any other disadvantage? I can probably give you one. Sorry. Methane cannot be produced. Okay. How do you make methane? Not produced. One carbon, not possible. Yeah.
So even number of carbons वाली reaction में example.
બધા even number જ હતા બેટા. Alkane produced has even number of carbons? 2 carbons. Alkane produced has 8. Having understood the drawbacks of Wood's reaction, I would try to take you to a very similar reaction, which is then the next part. Fifth type of reactions in the main title is Getting Alkanes from Alkyl Halides, in which I am showing you different ways of replacing halogen by hydrogen or getting an alkane. The fifth method is called Frankland's reaction. Frankland's reaction is exactly same as your Wood's reaction. No change. So there is nothing new accomplished as such using Frankland's reaction. Remember this. There is nothing new. But pay attention now. Why is Frankland reaction still done? In Frankland reaction, the same thing is accomplished in a very different way. We don't use sodium here. We use zinc. Frankland reaction is very similar to Wood's reaction, but the only thing is Frankland replaced sodium by zinc. Now there's a big advantage to this. There's a very big advantage to this. You have to heat the mixture and you will have RnR and ZnX2. He was able to effectively replace sodium metal with zinc. handling sodium or working with sodium is always very difficult. Imagine you want to produce something on a large scale and you're using huge quantities of sodium. It can be very, very difficult to do that. And therefore, when he replaced sodium with zinc, the reaction could be very, very easily done on a larger scale as well as on a smaller scale. And that made all the difference. So zinc was used in place of sodium, right, by Franklin. I can give you one simple example. Pay attention. CH2, 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 Pr and Br. This is 1,3 dibromo propane. Now if you use zinc and heat it, you end up in getting cyclopropane. Plus ZnBr2. Right? This still remained, a better way to accomplish Wood's reaction. So instead of using sodium, if you could use zinc and perform the same reaction, obviously the rate of reaction is slower, high temperature is needed, that's okay. But you still can accomplish the same reaction using zinc, which is a much better way of doing it, right? Okay. Still the problem of Wood's persists. What is the problem of Wood's reaction? Alkanes with odd number cannot be produced in pure form. Why? Because in order to produce an alkane with odd number of carbons, you need to use two different alkyl halides, and that is a big problem. Now, who solved this problem effectively? Without any problems, you could now react two different alkyl halides with no byproduct formation. You still get an alkane with odd number or even number or whatever, right? This was done by, later on it was accomplished by two people. The first one was called Corey, E.J. Corey, and the other one was House. The synthesis is called Corey-House synthesis, and this Corey-House synthesis made it possible to react any two alkyl halides and still get an alkane in pure form. So let us understand what this synthesis is all about. Corey-House synthesis. This is again a part which should not be done for the school exam, so don't worry. Whatever, Franklin is also not a reaction that should be done for school exam. So till now you have only two reactions done. One is with zinc. How do you reduce? And then the second one is Woods in that second category, right? First reaction you can do the full, right? From alkanes, alkenes, and cycloalkanes. Cycloalkanes are not generally given, but it's still okay. So let us take up Corey-House synthesis, the next one. This is the sixth reaction that we are doing. One of the best things would be an alkane with any number of carbon atoms can be produced effectively without byproduct formation. All right. So let us take up the first one. We can take Rx, Rx, and allow it to react with lithium, 2 moles of lithium. It gives us RLi plus LiX. RLi is called alkyl lithium. This is step number 1, Rx. Step number 2, I have to stabilize this. So RLi is made to react with CuI, but I take 2 times RLi with CuI. This gives us R2 CuLi plus the second Li combines with iodine. This is a very unique thing. It is called dialkyl, or we can write lithium dialkyl cuprate. This is also called Gilman's reagent, also referred to as Gilman's reagent. And once this is done, you can have the third thing. We can have R2, or look at this, R2 Cu and Li, Gilman's reagent, reacting with, look at this, R dash X, any other. The R and R dash combine here, any one R and R dash, and X would go out as X minus. So first of all, you will get R and R dash, 2 different alkyl groups connected, plus 1 R stays with Cu, and Li plus and X minus would form. This is the alkane formed. This is your alkane. So first of all, Rx reacts with 2 moles of lithium to form RLi. RLi would finally give you R2CuLi, and R2CuLi would again react with Rx to give you your final product. I'd give you, we could take up one of the examples and try to understand how this works. Pay attention. I start by taking any alkyl halide. Let us take up CH3, CH2, Br. Okay? And I'm going to put up, I'm reacting this with 2 moles of Li, and what should we get? What should we get? CH3, CH2, Li plus LiBr. Is that okay, everyone? Now what should we react CH3, CH2, Li with? We have to react it with copper iodide, right? But we take 2 of these. What do we get? CH3, CH2 2 times CuLi plus Lii. And now if I take CH3, CH2 2 times CuLi, this is ethyl lithium, and this is lithium diethyl cuprate, and this is supposed to be reacted with, let's say, any other alkyl halide, I'm taking a propyl bromide. And what would happen? One of the CH3 CH2s would combine with CH2, CH2 and CH3, giving you pentane plus CH3, CH2 and Cu, right? RCu, and you can have LiBr. This first product that you get is called a pentane. So we have effectively reacted which two alkyl halides? We've taken ethyl bromide and effectively reacted it with propyl bromide to finally get pentane. This is Corey House. You need to practice this a lot before you actually get hold of it. And that is why I have been telling you, write down these reactions on your own. Try to put down reactions on your own. When you get stuck up, just go through the book and then again do it. Once that is done, then try to do it again without seeing the book. Keep on 2 or 3 times and then it will be okay. And don't do 3 times at a go. Go through all the reactions once, then restart from the beginning. Then restart from not doing it 3 times. Because you tend to forget. But then it becomes mechanical. When you're doing it for the first time, you're very sincere. Second time, it's fine. And third time, it's just like fourth and fifth time, you don't even pay attention to it. Don't do that. It's one, and that is how you do it. See, the next thing that we're talking about is reduction of oxygen-containing compounds. I am talking about oxygen-containing compounds. They can be alcohols, they can be aldehydes, they can be ketones, they can be carboxylic acids, anything. Right? Using red phosphorus and HI. Now, this is the most versatile system. So, we can say any oxygen-containing organic compound can be reduced to alkane. So pay attention now. Here we are. We take up, let's say, an alcohol here, and we use HI. Very versatile system, and red phosphorus and heat. There are a few things that you have to know. All the oxygens would come out as water. And the alkane formed will have same number of carbons as are present in substrate. Whatever number of carbons are present in substrate, your reactant, the same number of carbons would be present in your product. Which means there is 1 carbon, so I would write methane. There is 1 oxygen, so I would write 1 H2O. Now count the hydrogens, 4 and 5 and 6. You have already got 4 here. How many left? So put a 2 here, and all the iodines that you get come out as I2. For example, if I take up ethanoic acid, I'm not going to balance HI first, just putting red phosphorus and heat. Pay attention. What do we get here? How many carbons do we have here? 2. So that will be 2 carbons, so it will be CH3 and CH3. How many oxygens do we have here? 2. So how many waters? Total hydrogens now 4, 5, 6, 7, 8, 9, 10. Here on this side you have 3 and 1, 4. How many left? 6. and the iodines come out as 3I2. Do you get this? Standard way of doing it. This is red phosphorus and HI. B, it is Clemenson's reduction. Used for converting aldehydes and ketones to alkanes. Clemenson reaction, aldehydes and ketones are converted into alkanes. Specific. How do we do this? Let us take up ethanol. How is this done? We take zinc amalgam, ZnHe, and HCl. Your CH3, CHO will become CH3, CH3, right? And oxygen obviously would come out as water. So it is zinc amalgam and HCl doing the trick. And then we have Wolff-Kishner reduction. What exactly is Wolff-Kishner reduction? Let us understand this. A Wolff-Kishner reduction would be taking, see, these reactions have to be done in detail in 12th standard. I'm just for 11th because they are not there in the book. You still need to know the basics of these reactions. Okay. Here, what we need to do is we can take any ketone or an aldehyde, anything. Again, first of all, this reaction is also used for converting aldehydes, ketones to alkanes. Here the difference is basic conditions. And there it is always acidic conditions. So while Wolff-Kishner is basic conditions, this is acidic conditions. What exactly happens here? We can take up a simple molecule like cyclohexanone, and we can allow it to react with something called NH2NH2. You must have done this in redox. This is hydrazine. And hydrazine, there is loss of water, H2O lost, to give you an intermediate. I'm not going to give you the name here because not needed. And this can be further heated in presence of KOH and ethylene glycol. Ethylene glycol. What is ethylene glycol? Ethylene glycol is the structure is ethane 1,2-diol. Other name for ethane 1,2-diol. It's an alcohol. So there is loss of N2. We get cyclohexane plus N2. So oxygen always comes out in form of water, like it came out here. It always comes out in form of water, and it is replaced by two hydrogens, making a cyclohexane. All good? Now, getting alkanes from Grignard reagents. Getting alkanes from Grignard reagents. Now, first of all, what is a Grignard reagent and what can it do? So, if you take a Grignard reagent, if you want to make a Grignard reagent, you have to take X. X can be chlorine, bromine, or iodine. And this can be treated with magnesium in presence of ether. They always write dry ether because Grignard reagent is very sensitive to, moisture. Now pay attention. You can get R MgX, or I can write down R dash MgX. This is your Grignard reagent. Here R is a partially negative, and magnesium MgX is on partial positive side. Right? R is negative. Now, this is called alkyl magnesium halide. And now, let me show you how this works. This negative R is so powerful in pulling out H plus. It always pulls out what? H plus. Pay attention. It can, you can take anything along with, you can react Grignard with anything in which hydrogen is connected to a more electronegative atom. For example, hydrogen connected to oxygen in water. Then this bond breaks. H plus will go to R and will become RH. If not this hydrogen, you can take hydrogen connected to OR. This is alcohol. Again the same thing. If not this, you take hydrogen connected to nitrogen. Let it be ammonia or anything else. Again the same thing. So you take Grignard and react it with ammonia, you take Grignard and react it with this alcohol, or you take Grignard and react it with water. Your product will be R of Grignard will combine with H and form an alkane. Pay attention, still more to come. H connected to S The same thing. H connected to any halogen. Same thing. Or it can be an H which is connected to an electronegative carbon. Which carbon is most electronegative? Pardon? Which carbon is most electronegative? Sp. Sp. So Sp carbon is this. A carbon connected to a correct carbon having a triple bond. And if hydrogen is connected to that carbon, again the same thing. Now all of this would finally give you what? RH. All of this would finally give you RH. What is this? This is water. This is alcohol. This is ammonia. This is hydrogen sulfide. This is hydrogen halide. Or this is a terminal alkyne. All of this would give you the same thing. Most of the times they use water or alcohol. Generally they use water or alcohol, but I anything where, see, if you have to remember, it is hydrogen connected to any more electronegative atom. Except carbon, wherever hydrogen is, it can be picked out. With carbon, only when carbon is a triply bonded carbon. Now someone talked about like, sir, આવું હોય તો શું કરવાનું? એસિડ હોય તો શું કરવાનું? ત્યાં તો H+ તરત જ નીકળે ને. કાર્બોક્સિલિક એસિડ હોય તો શું? એ તો થવાનું જ છે આવું. ક્યાં પ્રોબ્લેમ છે? કોઈ પ્રોબ્લેમ નથી. It's the same thing. H+ જોઈએ તમને. કેવી રીતે મળે H+? When H is connected to any other atom except carbon. With carbon, H can be removed, but it can be removed only if it is on triple bond. Right? So, if I give you a reaction like this, for example, let's take up CH3, CHBr, CH3. And if I ask you, what would happen if I add magnesium and ether? And you will get CH3, CH, CH3, MgBr. Here, this is minus and this is plus. Now, if I react this with water, or if I react this with alcohol or anything else, pay attention. If I react this with water, or let's say, if I react this with methanol or ethanol, people think, oh, આમાં શું આવશે? Ethanol છે તો કંઈ બીજું ના, કશું નહીં, એમાંથી H જ નીકળશે. તો બનશે શું? You will have CH3, CH. Now, this carbon will get H from here, so it will become CH2. And then the CH3. What would happen to MgBr? It is MgBr and OCH3. MgBr will combine with OCH3 minus to form MgBr OCH3. Is that okay? This is how Grignard can be reacted with, any acidic hydrogen. Hydrogen which can be removed as H+. You always get an alkane. Clear, Shah? So here we end. There is one more reaction, one more preparation to go, which is from carboxylic acid. And that we can take up next time.